In this screencast, we introduce the rotational equations of motion, and we're going to get these rotational equations of motion, which are second-order differential equations, on a rotational coordinate using Euler's first and second laws in combination. A classic example to apply this to is the disk rolling down an inclined plane that we see here. So first we need to attach our reference frames. The first reference frame we have is our inertial reference frame, which we define E1 along the line OP, E3 into the page, and we do this because our disk is rolling down the hill, which is going to be a clockwise rotation as we're looking at this planar motion, and then E2 being E3 crossed with E1. And second reference frame is our body frame. We place the origin of the body frame at point G, which is the center of mass of the disk, and then B1 is along OP when theta is equal to 0. So now we've defined the coordinate theta being clockwise between the axis E1 and B1, and then E3 in the same direction as B3, and then B2 is B3 crossed with B1. We have the relationship between these reference frames being theta dot in the B3 direction, so that's omega of B observed in I, and then the transformation between the two reference frames. Let's begin by applying Newton's first law, which we said is the sum of all the forces equal to the mass multiplied times the acceleration of the center of mass as observed in the inertial reference frame. So we need to define both all the forces that are on the body as well as the kinematics of how the center of mass translates. And so let's start with the kinematics. We define a position vector, rg, with respect to O, and this is equal to the coordinate negative x in the E1 direction. We differentiate this, so the velocity of g with respect to O as observed in the inertial reference frame is negative x dot in the E1 direction, and then the acceleration of the center of mass as observed in the inertial reference frame is equal to negative x double dot in the E1 direction. So we only had to differentiate x into x dot into x double dot. Now in this system we're assuming here that there's no slip on this wheel, and so because there's no slip or no bounce, that means that we can apply our constraint equation for this particular situation, and that's where we have x dot is equal to r theta dot. Now recall that we got that from understanding how a cycloid moves, and if the wheel is in contact with the ground, that the inertial velocity of the point P will be equal to 0. So that means that we can take the time differentiation of this to find x double dot. So d dt of x dot is equal to x double dot. And so our r is constant, it's the radius of the wheel, so this becomes r double dot. And so our acceleration, as observed in the inertial reference frame, of the center of mass is equal to negative r theta double dot in the E1 direction. So you can see we've taken care of everything on the right hand side because we have the mass multiplied times the acceleration, which we've now defined. So for the left hand side we need to find all the forces that are acting on the body, and so to do that we draw a free body diagram, and our free body diagram is of our disk, and apply all the forces that are on the disk. So there's our point G, and we have three forces that are applied here. We have the force due to gravity, which we'll call the vector m, and let's call the g a vector, mg. And then we have a normal force, which is perpendicular to the inclined plane, in the E2 direction. And then because there's no slip, in addition to the no bounce, then we have a friction force, which will enforce the no slip condition. So this is the force F, friction force, in the E1 direction. So far on each of our forces, we've defined our friction in terms of the inertial basis, our normal force in terms of the inertial basis, but we've put our force due to gravity, we know it's in the vertical direction, but we've put it in the direction of g. And let's make a vector, mg, let's call this uv, so it's a vertical direction vector. And we can use this to convert into a basis that we know, or that we've defined, which would be our inertial basis or our body basis. So let's do this. let's say we have UV. We know that's operating downward in the vertical direction. We have our E2 and our E1 as we've defined. And we have angles between these in which angle alpha and the angle alpha is here. And so we can define the relationship that UV, which is pointing downward vertically, is equal to a negative sign. So we're operating negative sign in the E2 direction, and then negative cosine alpha in the E1 direction. And so now this gives us the relationship of our gravity vector, or our force due to gravity, in an inertial basis when we apply this to our free body diagram. So we get negative mg sine alpha in the E1 direction minus mg cosine alpha in the E2 direction. And then sum all the forces together to get the force G. So it's our friction in the E1 plus our normal force in the E2, and then add to that the gravity vector, which is now defined in the inertial basis. We insert each of these expressions into Newton's second law, where our left-hand side is our force G, and then we're equal to our mass times the acceleration of the center of mass as observed in the inertial reference frame. And then with this we can separate these into our components. So we have our E1 component, and this is equal to negative mr theta double dot, and then our E2 component is equal to 0 E2 on the right hand side. And so we get two scalar equations that come from this expression. The first is a translational equation of motion, but it's in terms of theta double dot. And it's also in terms of an unknown F. We don't know the friction force. So we're going to have to find another equation to help us out here, which we'll get from Newton's second law. And then the second scalar equation that we get is our constraint force. So we get the normal force is equal to, when we pull this to the right hand side, of mg cosine alpha, which should make sense. The constraint force is going to stay the same, and it's based on the slope of the inclined plane. Now that we have this information, we move to Euler's second law, which we've defined as the time derivative, as observed in the inertial reference frame, of the angular momentum about the center of mass, as observed in the inertial reference frame, is equal to the moment due to all the forces about the center of mass. So we'll define each of these components and then solve, and we'll get a relationship in which we have F and theta double dot, so we can finish the equation of motion. So first let's solve for our kinematics, in this case, which is the angular momentum about the center of mass is equal to the mass moment of inertia multiplied times omega of the body as observed in the inertial reference frame. Now we've already defined for a disk that the moment of inertia is equal to 1/2 mr squared. And so here we can substitute in our angular velocity, which is theta dot b3, to get our angular momentum as observed in the inertial reference frame, is our moment of inertia 1/2 mr squared multiplied times theta dot in the b3 direction. And so taking the time derivative of this in the inertial reference frame gives us 1/2 mr squared will be constant, and so the only thing that we can differentiate here is theta dot. We'll differentiate that into theta double dot, and we're still in the b3 direction. And so this takes care of our left-hand side now, where we have the time derivative of the angular momentum. And so for the right-hand side, which is the moment about the center of mass, we go back to our free body diagram, and we define, as we did a couple screencasts ago, our moment is equal to the sum of all the forces, so force 1 through force n, of the cross product, so Ri with respect to G cross with each of the forces. So let's look at our free body diagram, and we see here that we have three forces. We have our friction force, we have our normal force, and we have the force due to gravity. And so we're calculating the moment about G, and we see that the normal force and the force due to gravity have a line of action through G. So it means the only force here that we're concerned about, or the only force that's going to create a moment about the center of mass, is the friction force. And the friction is operating at point P, so this is the cross product of Rp with respect to G cross with the force at P. The position vector of P with respect to G is equal to negative R in the E2 direction. And the force at P is our friction force, so this is F in the E1 direction, and the cross product then becomes the moment about G, negative R E2 cross with F in the E1 direction, and this is equal to positive R F in the E3 direction. Because it's a 2 cross 1 gives us a negative 3, and we're carrying through our scalar, or our negative scalar, R. So now we have the left-hand side of our equation and the right-hand side of our equation. We set these equal to each other, and we get 1/2 mr theta double dot is equal to F. And so now we have three scalar equations. The first two that come from Euler's first law, which deals with translational motion, and we have 2 degrees of freedom, 2 potential degrees of freedom in translation. And then we have Euler's second law, which then deals with our single rotational degree of freedom. And when we combine equation 1 and equation 3, then we get another equation of motion which says that theta double dot is equal to 2/3 G over R sine alpha. And so this is the equation of motion of the disk rolling down the hill. It's a second order differential equation, so we can integrate this once to get the angular velocity, and we integrate it twice to get the angular position given initial conditions. Now, another thing that we can do here is that we know that the relationship between the rolling degree of freedom and the translational degree of freedom is x double dot is equal to r theta double dot. And we got this from applying the no bounce, no slip condition. And so we could express this equation of motion, instead of theta double dot, we can express it in x double dot, so that x double dot is equal to 2/3 G sine alpha. So this is an alternative form for this equation of motion, in which we would only be concerned about the linear acceleration along the inclined plane.